Welcome back to this next video in which we are discussing the parathyroid glands and vitamin D. Okay, so the final thing we want to discuss is the mechanism by which 1,25-dihydroxyvitamin D is going to act on the gastrointestinal tract to increase the amount of calcium that it's going to absorb in the next meal, and also increase the amount of phosphate ions that are going to be absorbed in the next meal. Okay, so let's firstly start off with a little bit of a revision of the gastrointestinal tract. Like we did for the kidneys and the bone, I want to just draw a picture of the gastrointestinal tract. It's probably the simplest of all three of them. Most people know the basic structure of the gastrointestinal tract, but regardless, we'll start off with that little warm-up. Then what we'll do is discuss calcium absorption in the gastrointestinal tract, and we'll see the effect of 1,25-dihydroxyvitamin D on calcium absorption and how it's actually going to lead to an increase in that. And then we'll talk about phosphate absorption in the gastrointestinal tract and how, again, 1,25-dihydroxyvitamin D is going to lead to an increase in that. Okay, right, so firstly then, a little bit of a revision of the gastrointestinal tract. So the portion of the gastrointestinal tract that is going to be important for us when we're talking about calcium and phosphate absorption is, of course, the small intestine. However, I don't just want to draw the small intestine, I want to put, the structures that are on either end of it, to put it a little bit more in context. So we'll start our picture then with the bottom of the esophagus here. So here is the lower esophagus, here then is the stomach, like so, and then of course we go into the small intestine. So here is the first part of the small intestine, the duodenum with its classical C shape here. And now here is the junction between the duodenum and the jejunum. So the jejunum is the middle section of the small intestine here, and I'll draw it like so. And then here is the junction between the jejunum and the ileum. Now, this is a very nice, simple picture of the small intestine, and there is a certain amount of truth in this. The reason, of course, that when you're actually looking at a piece of small intestine in real life, within the mesentery, that it looks so much more complicated, is that actually these stretches of the small intestine aren't actually straight in this way. Instead, they fold up and down and up and down and up and down. But it does move in this way. This is reasonably accurate in that the duodenum stretches like this, the jejunum stretches like this, and then the ileum stretches like this. It just looks much more complicated because in reality, rather than just having straight intestine here, it would be curving up and down continuously. But it does overall move from side to side in this way shown in this picture. And then of course the ileum will end with the cecum here, and I'll put the appendix there, and then you'll go into the the ascending colon here. Okay, and I won't continue the picture on any further. So let's just highlight up the different portions of the intestine then, specifically the small intestine. So here in red, this is the duodenum, of course, and this is going to be an extremely important part for calcium absorption. So this is the duodenum. The middle part is, of course, then the jejunum. Okay, and I'll colour the jejunum in green, I think. So we'll have it in green, like so. And then the final portion of the small intestine is then the ileum, and I'll have the ileum coloured in blue here. Okay, so those are the three different sections then of the small intestine. Now let's actually talk about calcium absorption in the small intestine. So just like in the renal tubule cells, there are two mechanisms for absorbing calcium across the enterocyte cell epithelium. There is a transcellular route and there is a paracellular route. And just like in the renal tubules, both of those routes are made use of. Now the paracellular route, in which calcium moves from the lumen to the basolateral extracellular fluid, that occurs throughout the entire length of the small intestine. So if I now draw some enterocytes, so we have the exact same principle for enterocytes as we do for renal tubular cells, where there are two sides to the enterocyte cell membrane, an apical or luminal side and a basolateral side, and the two are not connected with one another. Well, they are connected, but they're not. Proteins in one side cannot move to the other side because of those tight junctions that surround the cells like a belt almost, and block the large proteins from being able to move from one side of the membrane to the other side of the membrane. Okay, now, enterocytes are a little bit more complicated to draw than renal tubular cells because of the fact that they have microvilli. So if you'll excuse me, I'm probably not going to bother drawing the microvilli on the apical side because they just make the picture look more complicated than it needs to be. Okay, so I'm just going to draw a plain box again for my cell here. Really, on the apical side here, of course, it should have microvilli, but I'm not going to bother drawing that. Okay, so this is the apical side then, like so, and this is the basolateral side. So of course, we are aiming to take calcium from the apical side to the basolateral side to absorb it into the body. Okay, so as I say, one mechanism this can occur is by the paracellular route, where calcium ions will move across the tight junctions, and they'll move, of course, only if there is a transepithelial electrical potential difference, where the electrical potential in the lumen is higher than in the basolateral extracellular fluid. Then there will be a drive, an electrical drive for the calcium ions to actually move to the area of lower electrical potential, which in this case is the basolateral fluid. Okay, and of course when you move those calcium ions, you'll then get water molecules following by osmosis. Okay, so calcium can be absorbed by the paracellular route all along the small intestine, so in the duodenum, the jejunum, and the ileum. Okay, so that's one means by which calcium can be absorbed. However, there is also a transcellular route, and the transcellular route is the one that concerns us because of the fact that it is this one that 1,25-dihydroxyvitamin D can actually affect, and is going to affect. It can't change the paracellular route, at least not as far as we know. Okay, so now let's talk about the transcellular route by which calcium can be absorbed across the enteric epithelium then. Well, what's nice here is that the means by which we're going to absorb calcium is exactly like the means that we reabsorb calcium in the kidneys, okay, by the transcellular route. So what we're going to have in the apical membrane then of our enterocyte is a non-voltage dependent calcium channel. So here, which I'll colour in pink here, is a calcium channel. And as I say, this is not going to be a voltage-dependent calcium channel, so its open probability is independent of voltage. And what's now going to happen is, of course, calcium ions are going to move down their electrochemical gradient into the cytoplasm of the cell. I'll remind you that the concentration of calcium inside all cells of the body is kept at a ridiculously low level, 100 nanomolar, far lower than it would ever be in the luminal fluid here. Okay, so you're always going to get calcium moving from the luminal fluid into the cytoplasm of the cell here. And also bear in mind that this will generally be down its electrical gradient as well. So calcium will move into the cell down its electrochemical gradient. Then, of course, this calcium that's arriving in the cytoplasm of the cell, it's going to have to then be moved across the basolateral membrane, and to do this we have the same array of active transporters that we had in the case of the kidneys. So we have a primary active transporter and a secondary active transporter. So I'll just remind you of this, it doesn't hurt to re-go over it. So there is the plasma membrane calcium ATPase, the PMCA, and remember that moves a calcium out of the cell cytoplasm in exchange for 2 protons coming into the cytoplasm from the extracellular fluid, and every time it does that, it hydrolyzes a molecule of ATP down to ADP and inorganic phosphate. Okay, so that's an example of primary active transport because it is using the energy that it gets from the hydrolysis of ATP to move that calcium against its electrochemical gradient. Then we have an example of a secondary active transporter, which is the sodium-calcium exchanger, which will throw a single calcium ion out, and in exchange it will bring in free sodiums. Okay, so that uses the sodium electrochemical gradient across the cell membrane, which favours the movement of sodium in to provide the energy for moving the calcium out. So that is an example of a secondary active transporter. So both of these active transporters, the primary active transporter, which is the PMCA, and the secondary active transporter, which is the NCX, are going to extrude calcium from the cytoplasm into the basolateral extracellular fluid, and overall we have now moved the calcium from the apical extracellular fluid to the basolateral extracellular fluid, i.e. we've absorbed it from the lumen, and this is the transcellular absorption of luminal calcium. And this just occurs in the duodenum, so this doesn't occur throughout the entire length of the small intestine. This just occurs in the duodenum. So the paracellular route is the entire small intestine here, whereas the transcellular route, this is just in the duodenum stretch of the small intestine. Okay, right, and it is this transcellular route that occurs in the duodenum that is going to be affected by the rise in 1,25-dihydroxyvitamin D in the blood in response to the parathyroid hormone. Okay, right, so now what's going to happen? Well, of course, 1,25-dihydroxyvitamin D is going to go into the nucleus of our enterocyte here. So if I just draw the nucleus of our enterocyte here, 1,25-dihydroxyvitamin D, once it has been created, is going to go into the nucleus of our enterocyte. There it's going to bind to the vitamin D receptor. The vitamin D receptor will then heterodimerize with the retinoid X receptor, and the vitamin D receptor retinoid X receptor heterodimer will then change gene expression within the cell. And which genes then are going to have their gene expression change that are relevant here? Well, in fact, what's going to happen is you're going to increase the expression of the genes for these apical calcium channels, and you're also going to increase gene expression for these active transporters in the basolateral membrane, the PMCA and the NCX. Okay, so all of the apparatus then that is used for transporting calcium from the luminal fluid here to the basolateral extracellular fluid, all of this is going to have its expression increased. And if we increase the number of apical calcium channels and the number of these active transporters on the basolateral membrane, and make sure that they go to the correct membranes, we're then going to get more calcium moving across the epithelium in this way. So that's the way in which we increase the transcellular calcium absorption in the duodenum in response to 1,25-dihydroxyvitamin D. So that is the way in which 1,25-dihydroxyvitamin D increases calcium absorption in the gastrointestinal tract. Excellent. Now let's talk about phosphate absorption in the gastrointestinal tract. So phosphate is only absorbed transcellularly, and it's absorbed transcellularly by enterocytes all the way along the small intestine. So the transcellular route isn't just limited to the duodenum as it was in the case of calcium. Okay, so once again, let me just draw an enterocyte here, and to keep things simple, I'm not going to show the microvilli. Okay, it just gets in the way if you draw the microvilli. It's then really difficult to draw things in the apical membrane. Okay, right, so once again, this is the apical side of our enterocyte, this is the basolateral side of our enterocyte, and our aim now is to transport phosphate ions from the lumen onto the basolateral extracellular fluid here. So how are we going to do this? Well, the transcellular route for absorbing phosphate is again just the same as it was in the kidneys. Okay, we're going to use the sodium phosphate cotransporter on the apical side, and then some mystery mechanism that isn't understood on the basolateral side. So again, this is just beautiful revision. So on the apical membrane then, we're going to have the sodium phosphate cotransporter, which is a secondary active transporter and which will use the electrochemical gradient of sodium across the cell membrane to move phosphate ions. Okay, so I'll colour in the sodium phosphate cotransporter then in blue here. Now remember, the sodium phosphate cotransporter had that clever but complicated mechanism where it could move phosphate ions in those two different states of protonation, it could move either of them. Okay, so it wasn't just capable of moving one of the phosphate ions in one of the specific states of protonation. It was actually capable of moving two different types of phosphate ions. It was capable of moving what we would strictly call hydrogen phosphate, HPO4 2-, and it was also capable of moving what we would strictly call dihydrogen phosphate, H2PO4-. Okay, now if it's going to move a hydrogen phosphate, HPO4 2-, then it has to move overall free sodiums with it. So the phosphate will be moved in along with free sodiums, and those free sodiums that you're moving into the cytoplasm of the cell, they'll be going down their electrochemical gradient, and they will be the things that are providing the energy to move the hydrogen phosphate ion here into the cytoplasm of the cell. Whereas if you're moving a dihydrogen phosphate, which has the lower charge note, you only need to move two sodiums into the cytoplasm of the cell down their electrochemical gradient to move that. Okay, so it requires less energy to move this one. Okay, so the sodium phosphate cotransporter is capable of doing both of these options. If it moves a hydrogen phosphate, then it will move free sodiums into the cytoplasm of the cell with that to provide the energy to move the hydrogen phosphate, whereas if it's moving a dihydrogen phosphate, then it will move two sodiums into the cytoplasm of the cell to provide the energy to do that. Okay, so in this way then it will overall move phosphate ions from the luminal side into the cytoplasm of the cell, and then by a mechanism that is not understood, the phosphate ions will then move across the basolateral membrane into the basolateral extracellular fluid. So I remind you that this mechanism, this transcellular absorption of phosphate ions, is occurring throughout the length of the small intestine. Okay, so we now want to understand how is 1,25-dihydroxyvitamin D, this activated form of vitamin D, actually going to affect this process, because we know that it's going to increase it. It's going to increase phosphate absorption. Remember, the idea being we want to replace the phosphate that the kidneys got rid of short term, because remember, this is occurring long after. This is occurring the next time we get a decent meal. Okay, so the kidneys dealt with the problem very quickly. Okay, they said, calcium's too low, let's get rid of phosphates so that we can raise free calcium ion concentration. But now, longer term, what we need to do is repair that temporary measure and bring the phosphate back up. So we want to raise phosphate absorption in the intestine. So 1,25-dihydroxyvitamin D is responsible for telling these enterocytes to do so. Again, what will happen is it will go into the nucleus of the enterocyte, it will bind to the vitamin D receptor, that will dimerize with the retinoid X receptor, and that retinoid X receptor, vitamin D receptor heterodimer, will then change gene expression. Now, which gene do you think is going to be upregulated? Well, of course, it's this sodium phosphate cotransporter. So you're going to upregulate the sodium phosphate cotransporter, and therefore you'll get more phosphate ions moved across the apical cell membrane here, and therefore also more phosphate ions moved across the basolateral membrane, therefore more phosphate ions absorbed. Okay, so that then is how 1,25-dihydroxyvitamin D, this activated form of vitamin D, is actually going to result in increased calcium absorption and phosphate absorption in the intestine. Okay, so overall, let's finally summarize what we have done here. So, if you become hypocalcemic, then the parathyroid glands are going to start releasing parathyroid hormone into the blood. Parathyroid hormone, very quickly what it will do is it will act on the kidneys to decrease the amount of calcium that we are excreting in the urine and increase the amount we're resorbing back into the bloodstream. Okay, so we do not want to be excreting our normal levels of calcium when we're hypocalcemic, so we stop any calcium being excreted in the urine. In addition, what we do is we start excreting more phosphate in the urine, so you get phosphaturia. Okay, so you reduce phosphate reabsorption in the kidney, in the nephrons. Okay, the purpose of that is that phosphate ions, they hog calcium ions in the blood. Okay, they bind calcium ions, and remember, we are trying to keep free calcium concentration constant. We need free calcium concentration to go higher. So one of the ways of doing that is to get rid of some phosphate ions, and then the calciums that they were bound to will then be free, and therefore will raise free calcium concentration. Okay, so as a temporary measure, the kidneys start getting rid of phosphate ions and lower the amount of phosphate ions in the bloodstream. In addition, what's going to happen is you activate this production of the active form of vitamin D. So we have circulating in our bloodstream inactive forms of vitamin D, which are the actual vitamin D molecules themselves, vitamin D2 and vitamin D3, then also the slightly more activated, or slightly further along the process of being activated, 25-hydroxy vitamin D molecules, and then finally, to make them into the activated form, we need the 1-hydroxylation reaction to be turned on, and this is performed in the proximal convoluted tubular cells, and parathyroid hormone stimulating the proximal convoluted tubular cells of the nephrons in the kidneys is going to lead to that final step occurring. So you're going to get 25-hydroxy vitamin D being turned into 1,25-hydroxy dihydroxy vitamin D. Okay, right, so now you've got both of these molecules to actually bring calcium up. So now 1,25-dihydroxy vitamin D, that's going to have that negative feedback effect on the parathyroid glands and stop them synthesizing further parathyroid hormone, because we've got enough now that the 1,25-dihydroxy vitamin D has been produced. Clearly parathyroid hormone is doing its job. Okay, and both 1,25-dihydroxy vitamin D and parathyroid hormone are going to act on the bone to increase bone resorption so that we can release calcium from the store in the bone and raise free calcium in the blood. Finally then, a more long-term effect is that 1,25-dihydroxy vitamin D is going to act on the small intestine, and it's going to raise calcium absorption at your next meal and raise phosphate absorption at your next meal. And the reason we want to raise phosphate absorption is, we're now returning back up to the correct calcium level. Okay, we're absorbing more calcium, so free calcium concentration is going to be going up. We might as well now use this as an opportunity to repair that temporary measure that we took, which was to lower phosphate level within the blood. So let's now bring the phosphate back up now that we're getting the calcium from the diet anyway, which can repair the damage of free calcium being too low. So we'll undo this temporary, slightly undesirable means by which we actually raised calcium, which was to get rid of the phosphate ions, now that we've got a better solution, which is to get more calcium from the diet. Okay, so that concludes our discussion of the parathyroid glands and vitamin D.